Hello, and welcome to the first video of our first class time series of lecture videos for the second semester of General Organic Chemistry. If you've had my course before, welcome back. If you're new to this course, I generally schedule these class time videos as short 10 to 12 minute presentations that are followed by questions. And then during the actual class time for the particular series of videos, we'll go through certain questions, review the material, and then at the end of each scheduled class time, there will be end of class questions. Hopefully, students will have learned the material well enough to answer those without too much trouble. So, in the second semester of organic chemistry, we'll start off with chapter 14, delocalized pi systems. And we have to ask a question: what effect does a pi bond have on the reactivity of a hydrocarbon? Well, first we've got to consider the simple system, the 2-propenyl or allyl system, and it's derived from propene. And this is a bond line structure of propene where our terminal methyl carbon has its 3 hydrogens explicitly drawn. And this brings up the idea of an allylic carbon, and that's the reactive carbon atom that's adjacent to the pi bond or the alkene in our propene system. It's that methyl carbon that has the 3 hydrogens attached. So we could think about plucking one of those hydrogens off, and depending on the number of electrons we have left behind, we have different systems, allylic systems, in fact. And so if we abstract a hydrogen and 1 electron, and we leave 1 electron behind, we form what we term an allylic radical. And for this bond line diagram, it not only exists as this particular radical, but we could go through a series of single-headed arrow pushing to arrive at this other resonance structure where our radical is centered at the leftmost carbon instead of the rightmost carbon. These are resonance structures. Hopefully students are familiar with how to create these. We'll review a little bit. Obviously today we're approaching how we draw resonance forms, and this brings up the idea of a resonance hybrid where we have this allylic radical, except that radical is delocalized among the carbons, and specifically our resonance forms suggest that that radical will exist either at carbon 1 or carbon 3, depending on how you number the skeleton, but not really at carbon 2. Of course, these resonance structures are a white lie. They're all not real. We have a deeper view of this reality, but we'll get to that in perhaps our last class time video in this particular series. So a resonance hybrid, of course, brings up an analogy. One might have, one structure that looks one way and maybe it's red, and another structure looks another way, and you could call that yellow. And the truth of the matter is you really have an orange molecule, something like that, right? It's neither one nor the other, but some superimposed hybrid of 2 different things. So let's continue forward. It's been a while since I've done this. What if we had taken the hydrogen and its 2 electrons? Well, we would form something called an allyl We'd have a sp2 hybridized carbon, it's trigonal planar, and there's an empty p orbital that I haven't drawn, and of course we get a formal positive charge at that carbon. Now we could create another resonance form by taking a double-headed arrow and pretending that we're moving these 2 electrons between maybe carbons 1 and 2 over to form a pi bond between carbons 2 and 3. Well, if we do that, we took them away from carbon 1, and lo and behold, now carbon 1 has a formal positive charge. There's our allyl cation. And of course, if you could have an allyl cation, you could have an allylic or an allyl anion, and that's if you pluck off a proton and leave the 2 electrons in that hydrogen-carbon bond back behind on carbon. And so here we have that illustrated. We've got these 2 electrons associated with this rightmost carbon, and because of the way we assign formal charges, we've got a formal negative charge on this carbon because it has 3 bonds and 2 electrons for a total of 5 things. Carbon has a valence of 4, so that's 1 extra, and so we've got to append a formal negative. To get to the other resonance form, we simply take these 2 electrons, pretend we're forming a double bond between this rightmost carbon, maybe call it carbon 3, and carbon 2, but if we do that, we have to push these 2 electrons in this double bond all the way over onto carbon 1. And so we draw the resulting resonance form, and we see that now carbon 1 has a pair of electrons and a formal minus charge. And of course, neither resonance form is the complete description of this allylic anion. They're both true somehow. And like I said, we'll see the deeper depiction of this system in perhaps our last lecture video. So a little bit of a review of arrow pushing if you didn't take this class with me, or if you've forgotten everything since the first semester. The tail of the arrow begins at the original location of the electrons. E is how I abbreviate electrons. The head of the arrow points to the destination of where the electrons are going. Double-headed arrows or double-barbed arrows denote 2 electron movement. Single-barbed arrows denote 1 electron movement. You would think that these are relatively simple rules, but it's always very tempting to draw your arrows with their tails beginning at atoms and pointing to where the atoms are moving. But the convention that we organic chemists use is the tails are drawn in the area of the electrons, and they're pointing to where the electrons go. So you might be tempted at some point to push atoms around, but we're really pushing electrons around. So try to remember that. All right. I will see you in the next video.